Hello students, today we are going to derive the moment of inertia of disk, and before that we have to know the moment of inertia of ring. After that we will discuss the theorem of perpendicular axis. Here just we recall the definition of moment of inertia. We have written one mathematical expression that I is equal to M.I.R.I square, where I varies from 1 to n if the body is consisting of m particles of masses m1, m2 up to mn. Distances, their respective distances are r1, r2, r3 up to rn. Then we have written this expression for moment of inertia and defined moment of inertia in this way. It is the sum of products of mass of each particle and square of its distance from the axis of rotation. For the sake of simplicity, we have taken n particles, but for the continuous distribution, we have written the same definition in expression form as integration of dm into r square, where dm is the mass element. It is situated at perpendicular distance r from the axis of rotation. So if instead of discrete distribution, means considering n particles, if we consider continuous distribution of mass, then we have to use such definition or such expression for moment of inertia, integration of dm into r square. So both these definitions are useful in deriving the moment of inertia of different bodies. But in our scope of syllabus, we have to derive only the moment of inertia of disk and note the moment of inertia of ring. So from these two relations, we note here moment of inertia of ring. It is moment of inertia of ring. This is our first point. It is equal to, I is equal to m into r square. So this is for a ring. First we here consider a ring in this way. So I will show here you a ring like this. This is a thin uniform ring. Its moment of inertia about its own axis is given by I is equal to m into r square. Own axis means here if we show axis like this, and if ring rotates in clockwise or anti-clockwise direction about this axis, which is passing through its center and perpendicular to its plane. Here axis is passing through its center and perpendicular to its plane. The ring can rotate in this way. So this is the description for the axis of rotation for the ring. And for that axis only moment of inertia is given by this relation. This relation is obtained from the basic relation or definition of moment of inertia. We have to only note this. Here m is the mass of ring and r is radius of ring. The ring is thin. We can show the ring in this way. Is like this. a ring. Actually it is thin ring, but for the proper representation here I have shown it like this, so that you can imagine it is a circular ring, even if slightly elliptical nature is shown here, but it is circular ring. Its center is O. Mass is distributed here like this, but average radius is R, because this thickness of ring or width of ring, if it is denoted by dr, it is very small, therefore R can be taken as its average radius. Now we will study or derive moment of inertia of a disk. For that, we consider the disk and show it in horizontal plane. So I will show here a disk like this. If it is held in vertical plane, its axis is horizontal. This axis is also its own axis, means passing through center and perpendicular to plane of this. This can be rotated in clockwise or anti-clockwise direction like this. It can be held in horizontal plane. I have shown it in horizontal plane, and the axis is vertical, its own axis. And for the disk, here mass of disk is considered as m, radius of disk is r. Then here we have to use one quantity, that its surface density, and it is denoted by sigma. It is given by mass upon area, and it is equal to m upon pi r square. So sigma for the disk is m upon pi r square. Now here I will show the axis of rotation. Now for the derivation of moment of inertia, we have to consider one element of disk, and that element is in the form of a ring. That ring can be shown here, which is concentric with the disk like this. It is having thickness or width as dr. Ring is having radius equal to r. This ring is called as elemental ring. It is representing the mass element, is elemental ring. So for this ring, we must have to note its area so that we can write its mass, because we have to use this formula, I is equal to integration of dm into r square. So we know r, it is the radius of ring, means axis, from the axis of rotation its distance is r. But for dm means mass element, magnitude of mass element, here dm, we have to write its area, surface area. It can be written as area of elemental ring. It is denoted by dA and it can be equal to twice pi r dr. Now we write mass of elemental ring. It is dm. It is equal to dm is equal to sigma into dA, because we have surface density means mass per unit area. Surface density means mass upon area or mass per unit area. Here you have to note for unit area, mass is sigma. Therefore, for the area dA, mass can be equal to sigma into dA. So here we have written mass of the ring as sigma into dA. So here dm can be written as sigma into twice pi r dr. So once we have the mass of ring, we easily substitute in the definition of moment of inertia or expression of moment of inertia. It can be substituted in this way. Here moment of inertia of disk can be I is equal to integration of dm into r square. Here for the integration we have to give the limit. The limit is from 0 to r, because we have taken one elemental ring here having radius r, but the disk is made up of the rings which are having radius from 0 to r. This r varies from 0 to r. This radius of ring can be slightly greater than 0 and its maximum value is r. So here this r value varies from 0 to capital R. So you have to consider these values as lower limit and upper limit of the integration, because here I have shown the disk of radius capital R. Here I have shown disk in this way, but this disk is made up of large number of rings and their radii varies from 0 to r. Here we have shown only one ring here which is having radius small r, but we have to give the limit. Here we substitute for dm, it is sigma into twice pi r dr into r square as it is. It can be having limit from 0 to r. It is equal to integration of, here we take constant terms outside the integration. One is here twice pi, sigma can be taken outside the integration, and we get here r into r cube dr. Integration varies from 0 to r. Now here we can proceed. I is equal to twice pi sigma and integration of r raised to 3 is r raised to 4 divided by 4, and its limit is from 0 to r. If we substitute for sigma we have written as mass upon total area of disk, it is m upon pi r square, and for r raised to 4 we substitute capital R, its power is 4 divided by 4 minus the lower limit we can substitute, it is as 0. So here the second term in the bracket is 0. We get I is equal to, here pi will get cancelled, 1 r square is get cancelled, and we get here mr square upon 2. This is the moment of inertia of disk about its own axis. We write here moment of inertia of disk. Here you have every time have to describe the axis. Here moment of inertia about its own axis. Its own axis. So when we write about the moment of inertia and rotational motion, always we have to describe the axis, where the axis is. Here this moment of inertia we have derived for about its own axis, means the axis passing through its center and perpendicular to its plane. Center here we can show by letter C, so that it can represent center of mass as well as center of disk. So just revise, here we have considered a disk in this way in the horizontal plane, but it is shown in figure like this. Center of disk is C. For the radius, its radius is r. Mass of disk we have taken as m. Then we have taken one quantity m upon pi r square is sigma. It is mass per unit area. Mass per unit area. Here clearly I can write here mass upon pi r square. It is the sigma, which is the surface density, or simply it can be mass per unit area of disk. From this value, we have used this value for the determination of mass of ring. Here ring we have considered any ring having radius r and width dr, but this radius value can vary from 0 to r. Initially we have written area of ring as twice pi r dr. Mass of ring dm is the sigma into dA, means mass per unit area into the given area dA here. Then dm we have sigma into twice pi r dr. By considering the expression for moment of inertia, we have written moment of inertia of disk. It is integration of dm into r square, but for the total disk, r varies from 0 to r. Here the next step becomes, here on substitution, it is integration of sigma twice pi r dr into r square, twice pi sigma taken outside the integration of r cube with respect to r, it is r raised to 4 upon 4. Substitution of limits in the next step. For the upper limit r raised to 4 upon 4, and for the lower limit it is 0. Here cancellation gives us the last step, I is equal to mr square by 2. It is the moment of inertia of disk. Now we proceed for the next point in this chapter. That point is theorems. Those theorems are used to determine moment of inertia of rigid body about the given axis. The given axis may, sometimes it is its own axis, sometimes it is the axis which is other than own axis. So for that, here there are two theorems. One is theorem or principle, theorem of perpendicular axis, and other one is theorem of parallel axis. Today we will discuss about theorem or principle of perpendicular axis, and in the next lecture we prove theorem of parallel axis. So here this theorem of perpendicular axis is used for laminar bodies or laminar objects. Laminar objects means those objects which are shown in a plane. It is two-dimensional object. So I have already shown you that this is a disk. It can be confined in a plane, xy plane, xz plane, yz plane, like this. So only two axes are sufficient to describe its dimensions. Similarly, here there is a rectangular sheet. It is also a laminar body, laminar object, because it is in a plane. We can show it in a single plane, and two axes are sufficient for the description of the body. Similarly, the ring, I have shown thin wire ring is there. It is also a laminar body. A coin, it is a disc. It is also a laminar body, laminar object, two-dimensional body. So here there is one body I have to show. I must have to show you that it is a paper, thin paper, and it is having irregular shape, not square, rectangle, circular. It is having any shape, but it is a laminar body or laminar object, because it is also can be described by only two axes, any two axes. So here this theorem of perpendicular axis gives the relation of moment of inertia about x-axis, y-axis as well as z-axis. Body occupies only two dimensions, but moment of inertia can be about the third axis also. So here we have to consider that point. So we consider the body like these paper cuttings, like this. It is having any shape. It is shown in a plane. If there is a point, say C, one axis is passing through it, is vertical, is shown by Z. One axis, another axis is passing through, again C is X axis, and here we show Y axis. So these axes are concurrent, they are intersecting at point C. Now for this we consider element at point P. This element is denoted by dm. Here the perpendicular distance of this element from the y-axis is x, and perpendicular distance of this element from the x-axis is y. Perpendicular distance of the element from z-axis is denoted by z, but it is equal to under root of x square plus y square. So you know that point. So there is no need of showing this distance. Simply we show the distance as z, and expression we use in the further discussion. Now here, if the body rotates about x-axis, then for the element dm, the moment of inertia can be written of lamina or body, moment of inertia of object, say object about x-axis is denoted by Ix, and it can be written as dm into y square, because perpendicular distance of dm from the x-axis is y. Similarly, we write moment of inertia about y-axis for the body of object here. It is Iy, it is integration of dm into x square. Here perpendicular distance is x. Here for the perpendicular we show the angles like this. Now the third point also we can write moment of inertia of object. Of course here it is laminar object about z axis, can be given by Iz is equal to integration of dm into z square. So if we have such moment of inertia, we can use it in theorem. Now theorem we state later, but we consider here this Iz. Iz is equal to integration of dm into z square, but z square here we substitute as x square plus y square. Then splitting the integration we get dm into x square plus integration of dm into y square. We get dm into x square is Iy, and integration of dm into y square is Iz of Ix. So Iz we got from simple geometry and concept of moment of inertia is Iy plus Ix, or it is Iz is equal to Ix plus Iy. So this is the expression. From this expression we can state the theorem of perpendicular axis. Moment of inertia of a plane laminar object about the axis perpendicular to plane is equal to the sum of moment of inertia about two mutually perpendicular axes in the plane of laminar body, and all axes are concurrent. So this is the statement. The theorem to determine the moment of inertia for the laminar bodies, and in the next lecture we will study theorem of parallel axis. So today we will stop here. Thank you.